last time we talked about how to measure variation. So measures of variation. So we said measuring variation was about measuring how spread out the numbers in a data set were from each other. So just as a review, how did we, what were some of the ways that we measured variation?
Standard deviation?
Yeah, so we ended up talking about the standard deviation. Well, we kind of built up to that, right? So we started talking about variance. And as a review, what does it mean to measure the variance of a data set?
Average squared distance from the mean.
Okay, very good. So the variance, by definition, is the average squared distance of each of the numbers from the mean. And remember we said it was a square distance and not just a regular distance. And because it's the average square distance, we try to undo that by taking the square root of the whole thing, and we call that the standard deviation. So the standard deviation is the square root of the variance and we said that by taking the square root, we're trying to undo each of the squarings when we go to find the average square distance. So in the end, it doesn't quite undo each of the squarings, so it ends up being approximately the average distance of each number from the mean. So the variance is exactly the average square distance of each number from the mean, and the standard deviation, being the square root of the variance, is approximately the average distance of each number from the mean. All right, so that's what we talked about last time. And so of these two measures of variation, which do you think is more commonly accepted or more accepted to measure the variance, or to measure the variation?
Standard deviation?
Yeah, why do you think that is?
Because when you take it's like, isn't the variance the one where you have to do absolute value? Or,
Yeah, so remember we talked about why you need to do this squaring? And we said that because you're trying to find an average distance, and the squaring will guarantee that it's a positive number instead of a negative number, because distance is a positive. And we said that the better way to make sure the numbers are positive is to take the absolute value, but we said that we're gonna encounter problems later on in other math disciplines, like calculus. If we try to find this average distance by taking an absolute value instead of squaring. So if we're resorting to squaring, then we said that this is something that we actually use to measure variation, but conceptually, we're measuring something we're not really used to, which is an average square distance versus an average distance. So if we take the square root, then it's approximating something that we're more familiar with, which is an average distance. So that's why, in practice, the standard deviation is more commonly accepted, because it's measuring something that is more conceptually familiar to us, which is an average distance as opposed to an average square distance. So the standard deviation is more commonly accepted. And it turns out that the standard deviation also has other interesting relationships So, let's review a little bit. So last time we talked about what it meant to be a bell curve. So you remember that if you have a certain variable, like IQ scores, we said that if you plotted the distribution of those IQ scores, then you would get something that looked like a bell curve. And what this meant is that there's some IQ score that is represented a lot in the population, where a lot of people have that particular IQ score. And as you move away from that particular IQ score in the center, then less and less people are gonna have that new IQ score. And so this distribution ends up being a bell curve because it is symmetric and it tapers off in both directions as you move away from the most commonly represented value. So this is an example of a variable that is distributed as a bell curve. So let's look at another variable. Let's say that, so besides IQ scores, we also talked last time about how there's some other variables that were distributed as bell curves. So what were some examples of other variables distributed as bell curves? Yeah.
Height.
Okay, very good. Heights in the population.
You said SAT scores?
Yeah, so we talked about how standardized test scores are distributed as bell curves, like ACT scores, like SAT scores. Good. So so height, SAT scores. What else?
Weight.
Yeah. Remember, we also said weight in the population. So let's do an example of one of those variables that's distributed as a bell curve, like weight. And let's talk about weights of men. And so let's say that I were to go out in the population and I would measure a whole bunch of men's weights. And then after I measure the weights, let's say I punch them into my statistics calculator, and the calculator will give me the mean and the standard deviation of a bunch of these numbers. So after I get all these weights, I'm gonna find the mean and the standard deviation from my calculator. And let's say the mean ends up being 180 pounds. And let's say that the standard deviation ends up being 20 pounds. So what that means is that there's a certain height of 180 here, where the most men happen to have. And as I move away from that weight in either direction, then it ends up tapering off and being symmetric on both sides, and ends up being the shape of a bell curve. That's not symmetric. Okay, so this is an example of a bell curve for weights of men. So, again, we're talking about in the context of why the standard deviation is more commonly accepted as a measure of variation. So what this is saying is that the standard deviation, or the average distance of each man's height in the population from the mean of 180 is about 20 pounds. So if you look at all the men and you find the distance of each man from the mean of 180 pounds, the average distance is approximately 20 pounds. And again, that's what we mean by standard deviation. So another relationship that the standard deviation has is there's a relationship between the percentage of the population that has a fixed number of standard deviations from the mean. So what I mean by that is, let's say we start with a mean of 180, and you look at all values within one standard deviation of the mean. So one standard deviation above the mean would end up being how many pounds?
2.
Yeah, so it would be 20 pounds plus the 180, which is 200. And what's one standard deviation below the mean?
160.
Very good. So the mean 180 minus the 20 pounds as one standard deviation, which would be 160. So it turns out that all these values between 160 pounds and 200 pounds represent values within one standard deviation of the mean. So this is within one standard deviation of the mean. And it turns out that for variables distributed in a bell curve, like weights of men in this case, then there's this relationship that all values within one standard deviation of the mean constitute a certain fixed percentage. And that fixed percentage ends up being 68% of the population. So it turns out that 68% of all men have weights within one standard deviation of the mean. So that means they weigh between 160 pounds and 200 pounds. And that constitutes 68% of the population.
Sorry, how'd you get 68%?
Okay, very good. So it turns out that this is true for any variable that's distributed in a bell curve. It turns out that this relationship is true for variables distributed in a bell curve. And this is not just a number I made up, but it turns out that any variable distributed in a bell curve, all values within one standard deviation of the mean will be 68% of the population. And so this is something that's mathematically proven, as well as empirically proven, which means just observed from experience. So this is something that's true for any variable that's distributed in a bell curve, including standardized test scores, including heights, and so forth. So it turns out that this relationship is true not only for all values within one standard deviation of the mean, there's a fixed percentage, but also any fixed number of standard deviations from the mean. So for example, if we do 2 standard deviations from the mean, then that's represented between what weight and what weight for values, for weights within 2 standard deviations of the mean.
140 and 220.
Yeah, very good. So if we subtract another 20 pounds and add 20 pounds in the other direction, then that'll be 140 as the lower bound, and the upper bound will be 220. So these constitute weights within 2 standard deviations of the mean. So this will be within 2 standard deviations. And it turns out that all values within 2 standard deviations of the mean, it turns out to be 95% of the population. And this is true for any bell curve. So that means that 95% of all men weigh between 140 pounds and 220 pounds. And only 5% of all men weigh anything outside that range. They're either, only 5% weigh either less than 140 pounds or more than 220 pounds. Any questions? So it turns out that this relationship between the number of standard deviations from the mean and the percentage of the population in that range, that relationship extends to any number of standard deviations and not just 1 and 2. So if we continue, 3 for example, so it turns out that within 3 standard deviations of the mean, that constitutes a certain fixed percentage, which is 99.7%. So that's virtually 100%. That's virtually everybody. So it turns out that 99.7% of all men weigh within 3 standard deviations of the mean, which is between what and what?
120 and 240.
Yeah, so another 20 pounds in each direction, because 20 pounds is 1 standard deviation, so it'll be 120 pounds to 240 pounds.
0.3%, let's go.
So that means that 99.7% of all men, virtually 100% of all men, weigh between 120 pounds and 220 pounds. And only 0.3% weigh anything outside that. Any questions? So this is true for any bell curve. And basically you only have to capture the correct mean and standard deviation, and then you can make these generalizations. So let's practice an example. So let's say that I gather a whole bunch of data points, and then I have a whole bunch of numbers, and I punch the numbers into my calculator, and the calculator will give me the mean and the standard deviation. So let's say that the mean is 50, and the standard deviation is 10. But of course, this is only a sample of all the data points I just gathered. I want to know what percentage of the entire population, from which I haven't seen yet even, so what percentage of all, which is population, data points, have values between 30 to 70. So just from these summary statistics, what conclusion can we make about what percentage of all values are between 30 and 70?
It's within 2 standard deviations due to it being a distance of 20 from the mean, and each standard deviation is 10, therefore it would be 95%.
Okay, excellent. So let's let me basically repeat what you said, and I'll fill in some gaps. So the main thing is that we talk about this important relationship between the percentage of values within a fixed number of standard deviations from the mean. But remember that this only applies to bell curves. So this only applies to variables that you know are distributed in the shape of a bell curve. So we can use that bell curve relationship if this data happened to be distributed in the shape of a bell curve. So the first thing we need to do is we need to, the data that we just collected, we need to plot the histogram to make sure it's distributed in the shape of this bell curve. So let's say that we do that. Let's say we plot this distribution, and we see that it's in this shape. So this looks like it's in the shape of a bell curve. And again, this is only for the sample data. So if the sample data looks like it's distributed in a bell curve, then you can reasonably assume that population data will also be distributed in a bell curve. So because of that, now you can use this bell curve relationship that we just talked about. And so this mean of being 50, going from the mean to each of these boundary points, now we have to go in how many standard deviations do we have to travel from the mean to each of these boundary points. And so going from 50 to 70 is a distance of how many units? Yeah, 20 units. But we know that each one standard deviation has 10 units. So therefore, how many standard deviations are we traveling from the mean to this boundary point of 7? Yeah, 2. So because there are 10 units in each one standard deviation, 20 units would constitute 2 standard deviations. So this equals 2 standard deviations. Any questions on that? And the same thing in the other direction. So going from 50 to 30, we're going 20 units, and there are 10 units in each one standard deviation, so therefore we're traveling 2 standard deviations. So all these values between 30 and 70 are said to be within 2 standard deviations of the mean. Yeah.
So the percentages for each of the standard deviations is gonna stay the same regardless of the problem? Like-
Yeah, regardless of the problem, because it's a bell curve, we only think in terms of the number of standard deviations from the mean. And any bell curve within 2 standard deviations of the mean, regardless of the problem, the percentages will stay the same.
Oh, okay.
Yeah.
It's like half of, if you're like within one standard deviation, but you're only like going from 160 to 180, can you say it's like 34%? If you're just like examining half of it?
Yeah, if it's actually a bell curve, then yes, it's symmetric, and you can actually say that this entire thing is 68%, so half of it is 34%.
Right.
Because bell curves are symmetric. Good question. Okay, any other questions you guys have? Okay, so because all these values are within 2 standard deviations of the mean, and this variable is distributed as a bell curve, then you can use this bell curve relationship, and you can say that all these values are, because they're within 2 standard deviations of the mean, this constitutes 95% of the population. So these values, all the values between 30 and 70 end up being 95% of all the values.